Hello everyone, welcome to Signals, Systems, and Signal Processing with Wolfram U. The topic of this lesson is elementary signals. This lesson covers some of the very important signals that are used in different places in signal processing, either as building blocks for more general and complex signals or for describing and analyzing systems. These signals are sinusoidal signals, exponential signals, unit step, and unit impulse or unit sample. We will discuss each of these classes of signals in continuous time as well as discrete time, and we will look at their differences and similarities in both cases. Let's start with sinusoidal signals. Sinusoidal signals are expressed mathematically in the general form A sine of omega t plus theta, where here A is called the amplitude of the signal, omega is the frequency of the signal, and theta is the phase of the signal. Plotting the sinusoidal signal, you can see how they change over time. Using a manipulate object as seen here, you can see how changing these three parameters affects the shape of the signal. If you change the frequency, for large values of frequency, you have larger number of variations in a certain time interval. As you change the amplitude, for the smaller values of the amplitude, the range of the signal is smaller, it is reduced in magnitude, and for larger values, the range is larger. Changing the phase starting from theta equal to 0, if the value of the phase is decreased in the negative direction, the effect that it will have on the signal is that it will shift the signal to the right. Now let's look at the discrete time sinusoidal signal where x of n is defined as sine of omega n plus theta. The difference here is that the independent variable or the time variable n can only take integer values. Plotting x of n shows the sequence, and if you track its envelope, you can see clearly that it follows the same sinusoidal form as in the case of the continuous time sinusoid. Also, changing the frequency has the same effect. Changing the amplitude causes the same signal magnification or reduction. And again, here, changing the value of the phase shifts the signal horizontally. So these two cases are very similar. They, however, have very significant and important differences, which we will discuss next by going through some of their properties. The first property is periodicity in time. Continuous time sinusoids are periodic. In general, for a function to be periodic, it means that there must be a non-zero value capital T such that f of t is equal to f of t plus capital T. For sine, this equation will be as indicated here. And for sine function, we already know that adding an integer multiple of 2 pi k, to the argument gives the same sinusoidal function. Comparing these two equations, it will be clear that omega t must be equal to 2k pi, or t is equal to 2k pi over omega. To get the smallest such number for period, we replace k with 1, and so the period of the sinusoidal function sine of omega t is 2 pi over omega. We can also express the angular frequency in terms of t as 2 pi over t. And the frequency f in hertz is equal to 1 over capital T. Finally, omega can be written in terms of f as 2 pi f. Now, let's look at the periodicity in the discrete time case and see that things are not exactly the same. For a sequence x of n to be periodic, there must be a non-zero integer value capital N such that x of n is equal to x of n plus capital N. Repeating the same steps as we did for the continuous time here, n must be equal to 2 pi k over omega for x of n to be periodic. So far everything seems to be the same as the continuous time case, except that here this value must be an integer number, and that may not always be the case. So if we can find a value of k such that 2 pi k over omega is integer, then we say that x of n is periodic, and the period is capital N. In other words, for sinusoidal sequences to be periodic, omega must be a rational integer multiple of 2 pi. And if omega cannot be written as 2 pi k over n, then x of n is simply not periodic. So again, for periodic sequences with period capital N, the frequency must be a rational integer multiple of 2 pi, or an integer multiple of 2 pi over capital N as shown here. The quantity 2 pi over n is called the fundamental frequency of the sequence x of n, with k being 1, 2, 3, and so forth. We call two sequences harmonically related if their frequencies are integer multiples of the same fundamental frequency. For example, let's look at all cosine sequences with period n equal to 8 with frequencies given as indicated here, k changing from 0 to 11. Note that starting with k equal to n or 8 in this case, the sequences are repeated and not distinct anymore. In general, the number of distinct harmonically related sequences is finite and is equal to the period n. And remember, this is a property of discrete time sequences and does not apply to continuous time signals. Next class of signals are exponential signals. Continuous time and real-valued exponential signals are mathematically expressed as r to the power t, or more commonly as e to the power minus at, replacing the base r with e to the power minus a. Here the parameter a is a real scalar. Plotting the signal shows that for negative values of the parameter a, we have a growing exponential, and for positive values of a, the function decays exponentially. The higher the value of a, the faster the signal goes to 0. Discrete time real exponential sequences are expressed as r to the power n, where r is a real number. Plotting the signal, you can see that for positive values of r, which are less than 1, the signal decays geometrically. And when r is greater than 1, r to the power n grows geometrically. Also note that for real exponential signals, e to the power minus a was always positive. Here, r could also be negative. For negative values of r, the signal alternates in sign for odd and even values of n. If the parameter a is a complex value, then we call the signal a complex exponential signal. So complex exponential signals are specifically expressed as shown here, where j is the square root of -1, an imaginary number, and omega is a real positive scalar. Note that we can always rewrite an exponential expression using the Euler's identity in terms of sine and cosine, as shown here. So basically, we have a complex signal that is sinusoidal in its real and imaginary parts. That's what the plot of the signal shows as well. The real part and the imaginary part for varying values of frequency are two sinusoids that are out of phase by pi over 2 or 90 degrees. They are cosine and sine. When two sinusoids have the same phase, we say that they are in phase. Otherwise, we refer to them as out of phase. The amplitude of the sine and cosine is decreasing exponentially for positive values of sigma. Similarly, for the discrete time complex exponential signals, we can write the function as shown here. And again, this is basically scaled sine and cosine for the real and imaginary parts. Plotting the signal shows that the amplitude of both the real and imaginary parts decay exponentially. The third and the final set of class of signals that we will discuss in this lesson are unit step and unit impulse. The continuous time unit step function is defined as 0 for negative values of t, and it is equal to 1 when t is greater than or equal to 0. The discrete plot of the sequence also shows these values. Note that the function is discontinuous at t equal to 0 and mathematically is not differentiable at t equal to 0. To define the unit impulse, first consider this rectangular signal whose width is delta and its height is 1 over delta, which means that the area of the rectangle is 1 for all values of delta. The unit impulse function is defined as the limit of this rectangular signal as delta goes to 0. That means that it is a rectangular signal with the width 0 and the height of infinity. This signal is denoted by delta t, and to plot the signal with the height of infinity, we choose to use an arrow, and the number 1 next to the arrow gives the area of the rectangular function. So again, the unit impulse is a signal that is 0 everywhere, except for at t equal to 0, where it goes to infinity. And if we take the integral of the signal, it will be equal to 1, as the area under the curve for this function is 1. Let's look at a few other properties of the unit impulse function, which will make it easier for us to work with the signal. If delta t is multiplied by any function f of t, since delta t is 0 everywhere except for t equal to 0, the result will be equal to delta t times the value of f at time 0. This property is called multiplication by a function. Now, if you take the integral of this product, the result will be f of 0 times the integral of delta t, which is 1, and so this integral is equal to f of 0. A more general form of this equation can be written as indicated here with a shifted version of the delta t minus t0, which is non-zero at t equal to t0, and therefore the integral will be equal to the value of f at t0. This formula is called time translation. Let's look at an example where we want to compute the value of this integral. The integrand is delta t minus 3 multiplied by an exponential function e to the power minus t. Comparing this expression with the integration in the time translation formula and replacing f of t with e to the power minus t and t0 with 3, the integration can be simplified as f of t0 or f of 3, which is e to the power minus 3. We can verify this result using the Wolfram language by evaluating integral of e to the power minus t, Dirac delta, t minus 3, t going from 0 to infinity, which gives the same result. The unit impulse and the unit step function, are related mathematically. The unit impulse can be obtained by taking the derivative of the unit step function ut. And the unit step function ut can be written as the integral of delta tau d tau, tau going from minus infinity to t. Let's test this also using the Wolfram language, taking the integral of Dirac delta t with respect to t gives Heaviside theta of t. Now, Heaviside theta is another way the step function can be defined. It is defined as 0 for negative values of t and 1 for positive values of t. The difference with the unit step that we saw before is that it is not defined at t equal to 0. In the Wolfram language, Heaviside theta is used since it has better algebraic properties with respect to differentiation and integration. In discrete time, the unit step at n is defined as 1 for values of n, integer values of n that are greater than or equal to 0, and it is 0 elsewhere. You can see these values in the plot of the function as well. The unit sample, delta n, or delta sub n, also known as Kronecker delta in the Wolfram language, is defined as 1 at n equal to 0, and it's 0 elsewhere. Plotting the sequence shows these values. The only non-zero value is at n equal to 0. Unit sample located at n equal to n0 is the shifted version of the unit sample, and it is therefore 1 at n, where n minus n0 is equal to 0, or at n equal to n0, and it is 0 for all other values of n. Plot of delta n minus 2, for example, shows a unit sample at n equal to 2. Note that for any given sequence, in general, we can express the sequence as a weighted sum of unit samples. For example, the sequence shown here can be expressed as sum of shifted sample sequences delta n minus n0 with coefficients that are equal to the value of the sequence at each point n0. For this example, x of n would be 1 times delta n plus 2 times delta n minus 1, and so forth. As in the continuous time, unit step and unit sample are related mathematically. The unit sample is the first difference of the unit step, which means that it is equal to the unit step un minus the unit step delayed, or un minus 1. And the unit step un can be written as the sum of unit sample delta m going from minus infinity up to n. In summary, in this lesson, we studied a set of very important signals which are shown here in both continuous time and discrete time. In future lessons of this course, these signals are going to be used frequently, and so it's very important to understand these signals and to remember their basic properties.